So this week we're going to be looking at the transistor in weak inversion or so-called sub-threshold regime of operation. And disclaimer, I'm taking the slides from last year. These are the ones that Toby made. We are usually swapping lectures, and so this is all of Toby's slides. Yeah, so we'll go over the history of the MOSFET and then just summarize quickly again a review of semiconductors and go into the details of what is a metal oxide semiconductor field effect transistor and what is complementary metal oxide semiconductor technology. And then look at the physics of transistors and how they are, in subthreshold in particular, how they are essentially the same of the physics of nerve membrane channels and what is the relationship. Then we'll also look at the MOS capacitor, which is also a very important structure that we actually ask at the exam every time. So you should pay particular attention to this part here. And the various regions of operations of a transistor and capacitive dividers will actually figure out where this kappa term that you'll see coming up over and over again, where does it actually come from? And then, yeah, basically use the transistor in subthreshold. So again, at any point, just interrupt me if anything is not clear. Just ask questions any time, or just to clarify or discuss. It's nice if it's interactive. So the history of the transistor goes back to many decades ago. It's actually the theory of how transistors should operate was proposed in the 30s. And this was before any transistor had any MOSFET had been ever discovered or implemented. And only in 1947, it was actually fabricated. This is a picture of the original device that was fabricated in 1947 at Bell Labs by Bardeen, Brattain, and Shockley. And it was basically a breakthrough because it was a solid state device that would actually implement all of the equations that were hypothesized and predicted in the 30s. This was sort of a research environment device. It was really looking at semiconductors and connecting pieces of doped silicon together. The commercialization of transistors actually became available only in the 70s. So your first calculators, well, not yours, but your grandfather's first calculators, the first solid state radios and all those things started to appear only in the 70s. So if you think about it, it's really, really recent. It's just a few years ago that we started to have integrated devices. So devices that were integrated on a single piece of silicon, many together. And from that point on, the history of how Intel started producing microprocessors and how in the garage of Silicon Valley, Apple came about, and then Microsoft and IBM and so on. So it's really basically due to this discovery from the 50s until the 70s, and then that led to this revolution that we are now taking advantage of with all these devices that we are using. And it's all due to the single device here, the field effect transistor. And if you take a piece of silicon and this is a cross section, so you have to imagine there are these 8-inch wafers, they're polished piece of silicons that have a little bit more donors or a little bit more acceptors. And you take a cross section, and then you look at the type of things the type of structures you can fabricate. These are essentially p-n junctions. So from the first lecture, you just dope with higher concentrations of donors to get n+ regions. You dope with maybe less concentrations of acceptors to get p- regions. And then you can create these p-n junctions. And that's sort of the fundamental element that allows you to build these field effect transistors. But the other important part that you need is to have a very thin and well-controlled channel that is insulating, separating the semiconductor, which is your silicon, from your conductor. And the conductor, in this case, it's the gate. And it's implemented using polysilicon. So polysilicon is actually, a highly doped semiconductor. It's actually a conducting, so equivalent to metal. And by having these p-n junctions and then this very well controlled thin oxide here, then you can really create this field effect transistor. And we'll see now how it works. Now, in complementary metal oxide semiconductor, you always have the two complementary types of devices. The N-type devices, it's denoted N-type because the source and the drain regions are doped with more donors, so you have more electrons. And the P-type devices that are doped with more acceptors, so you have holes flowing through the channel. So here you have a source of electrons, that's why it's called source. So you have more electrons than you have in the substrate, and then if you have conditions are right, you can have electrons flowing through the channel on the surface, essentially, of your silicon wafer, from the source to the drain. And in this case, you have a lack of electrons, so holes, again, flowing on the surface, just at the very, very top, between the source and the drain. In order to, is there a question?
Yes.
Yes.
Quickly, why is it called N+? There are more electrons. Doesn't make sense. The plus sign.
Oh, it denotes the amount of concentration. So the minus and the plus in this case is not the sign of the charge. It's actually how many more donors you have. So it's highly doped. It means there's a lot of N-type elements. So the plus and the minus is just to denote how much concentration of those things it's there. So it's lightly doped if there's a minus. You could have N minus, like here it could be N or N minus, or P minus or P plus and N plus. So the plus and the minus are not referring to the charge, but to the amount of concentration or the intensity of concentration. Yes, so depending on the P and the N, you have a P-type or a P-FET or an N-FET. In order to have P-FET, however, you also need to separate the P plus region from the P minus region. If you just would put P plus directly in the P substrate, you would have an ohmic contact. And so you would basically just short whatever is the value of the voltage that you're using for this P substrate, which is typically ground. You would short that with the P plus region. So in order to separate the voltages that you have, on the source or on the drain from the ground, which is the reference level of the P minus, you need to have another layer, which is called the N well. So basically you diffuse donors again, maybe at lower concentrations than the active areas. So this green part is called the active region. The yellow part is called the well. You diffuse those, and because you're diffusing them, they sort of spread out in a less controlled way. So they sort of, spread to the sides, but also they go deeper. And then you can have your active areas here with PN. So you have a PN junction here, and you have a PN junction here, or an NP junction here. And depending on the voltages, you can have them conducting or in forward or reverse regions. So those, yes.
And does it have to be an N well in a P substrate, or could it also be the other way around?
Typically, in the early years, you had both types. You could have a wafer that was N substrate, and then the default would be a P-type transistor without having to have extra wells, and then you would need to do a P well in the N substrate to do the N-FETs. In the first maybe decade of CMOS electronic design, everything converged to having only P substrate. So if you just want to make a chip yourself and you go and shop for a factory that is making these things, you will only find P substrate possibilities. So typically, in practice, just from commercial perspective, you always have to use a P substrate and N-well strategy to do P-type. But it could be both in principle. It depends. In fact, actually now in the more advanced processes, there is some concentration, typically it's P, but then you could have an N well or a P well. You could actually have a more highly concentrated region, which would be a P well, to have your N-FETs in a P well, not just in the substrate. And the most advanced technology, which it just came out a few years ago, mainly in Europe more than in Asia or the States, is called fully depleted silicon on insulator, which means that your substrate is not silicon, it's just an insulator, and then you have to put your own wells in between. So if you want to make an N-FET, you have to put your P substrate or your P well, If you want to make a PFET, you have to put your N well. So in this FDSOI process, fully depleted silicon on insulator, you have to put your explicit wells for both types of transistors, because the underlying background is just an insulator. This is just details, but the only thing you have to remember now is that NFETs are denoted by the fact that the active region is N+, and PFETs is denoted by the fact that the active region is P+. And again, this is a cross section. So if you're looking at it from the side, if you look at it from the top, when you're doing layout, you're actually trying to define the transistor so that the company can fabricate it, you would see something like this square here, where you have the background is gray, and then your active areas are these green areas here, and then your gate, your polysilicon, is this red area here. And this is the way that the transistor looks when you're actually drawing a layout. Yes?
In the last slide, what's the field oxide for?
The field oxide, this is the gate oxide is this very, very thin insulating layer that is insulating the semiconductor from the conductor. The field oxide is the same. It's the same. It's this SiO2, silicon dioxide. It's just that it's not controlled by the masks. It's allowed to grow. And so the part of the oxide that is not thin is called field oxide. And it's usually just everything that is around transistors that is sort of separating the semiconductor from whatever is on top. If it's a transistor channel, it's called the gate oxide. It's exactly the same, SiO2. It's the same material. And if it's not under the masks that are controlling the thickness, it's allowed to grow. In fact, it oxidizes just with oxygen. It gets bigger, and then it's thicker. That's why it's drawn like that. Yeah. So here you see the example of the N-type, and again, where you have the masks that control, the source and the drain region. Through etching, you actually even etch away through some chemical process the thick part. You have a very well controlled thin part, and then everything else that is not part of the device is left, uncontrolled, and it can grow. Yeah, and this is an example of what when you deposit polysilicon on top of your very thin gate oxide, this is what it would look like in reality, in practice. This is the way we draw it, but when you actually fabricate it, you see that there are all these imperfections that just come out of the fact that it's a physical device that is being fabricated through some lithographic process with, bombarding things with ions and then etching things away and then masking them and so on. The process is quite complicated. But this is just to remind you that it's a physical device that has some geometry and has imperfections. Every transistor, even though they're drawn identically on your computer, they are different from each other. Yes? Thick oxide and field oxide. Is that the T that you mean? Yeah. Yes, thick oxide. I think someone has their mic open on Zoom. Yes.
But didn't you just say that the gate was thin?
Oh, sorry, thin oxide. Sorry.
Okay, also irgendwas zwischen
thin oxide and field oxide.
Okay.
I don't know how to ask.
No, you can use it.
I have to check for the participants. Yeah, okay, I know who it is. Sorry for. Oh no, because I'm not the host, but maybe I can just ask. Christian, could you mute yourself? I know who you are. Okay, maybe he left his office. Anyways, now if we look at the symbols of the transistors, they are basically drawn, you already know, but this is just a reminder. They're basically drawn as these in the schematic diagrams. Here it is. For the NFET, you have these, basically this drawing here. Older circuit diagrams have the arrow. but in most of our circuits, we'll just use this. The top here is the gate. So this these two lines denote the fact that you have an insulator. So it's like a capacitor. And then the gate is in the middle. And then on the side, you have the source and the drain. It's a perfectly symmetrical device. So the source and the drain could be interleaved. It's just a matter of definition and which one is the source, which one is the drain. So in NFETs, the source is the one at the lowest potential and the drain is the one at the highest potential by definition. And vice versa in PFETs, you're always flipping sign. And PFETs is the same symbol. In the older schematic diagrams, you might see these arrows pointing in. The gate is on the bubble. There is this bubble to denote that the majority carriers, so the things flowing in the channel, are not electrons, but is lack of electrons, it's holes. And so this is just to remind you. So this is a PFET symbol, this is an NFET symbol. You'll see lots of them in the class. And the terminals are denoted VG, VD, and VS for gate, drain, and source. The source is the source of electrons, as I told you. The drain, just by definition, is the one that is at higher voltage. I think maybe I said it wrong the other time, but the correct definition of the drain is the one that is the higher voltage for NFETs and the lower voltage for PFETs. And the source is the one at lower voltage for NFETs. We'll see what what effect having voltage on the gate has on the transistor, and we'll see the effect of changing the D and the S, the source and the drain. For now, this is just terminology. So just the definition, again, apologies for the confusion. VD is the one at the highest potential in NFETs, and PFETs is the other way around. You just need to remember to switch the sign. Okay, so if there are no more questions on the basic definitions of field effect transistors, we'll now look into the physics. How do these devices work? And again, in order to remind you how they work, we'll first look at the P and the N devices or materials and PN junctions. So in order to do that, we need to take a piece of intrinsic silicon, meaning that it's a pure crystal, and then we need to dope or add extra donors or extra acceptors. And as soon as you do that, your intrinsic semiconductor becomes extrinsic. And so when you have extra donors, it means that you have ions that have extra electrons that are free to flow in this crystal. And when you have extra acceptors, you have basically fixed negative charges and then lack of electrons that are allowed to flow through the crystal. So you have these plus charges that can move around freely in the semiconductor. So the way to denote this is to say that the majority carriers in P-type devices, P-type material are holes, and the majority carrier in N-type materials are electrons. And the other thing is when we see these drawings, the gray bubbles here, these gray circles, are fixed charges. So they're stuck in the crystal. They're like really ions. And then the white ones are the mobile charges. Those are the ones that can move around. So once you have this, we can look at energy band diagrams. So, you know, there are, by looking at materials, you know that insulators have a very large energy gap between the valence and conduction band. Metals have it overlapping, and semiconductors have a little gap between the valence and the conduction band. And if you just draw your band diagram, you can then put, you know, the limit of the valence band. So you would have a lot of energy levels that go from EV down, and then the limit of the conduction band, and you have a lot of energy levels that are free from EC up. And then you have this gap that is between the valence and the conduction band. And the one that would denote the equilibrium is the Fermi level. It's this EF. And this is just from pure physics. The concentration of holes and electrons is the same, and it's equal to N. I think this should be N square, Ni square. I think the 2 went down. So the product of NP is equal to Ni square in intrinsic silicon. Now, if you have N-type silicon, you essentially basically increase the number of free electrons, the mobile charges, and so you increase the concentration of donors. So you have this formula that tells you if you have an N-type silicon, what is the concentration of majority carriers, which are the electrons. And it's essentially, it's a number that is given by the physics of the device, how many donors you actually injected into it. And it then is proportional, you can actually derive it, is proportional to this exponential, the difference between the Fermi level and this intrinsic, what would be the intrinsic Fermi level. So this difference here is giving you, if you take the exponential and you multiply, is giving you the extra amount of donors that you have, or mobile carriers. And the same you can say for the p-type silicon. It's just the other way around, and you can write the concentration of holes as this exponential. So these exponentials are important. It's really important to remember that because we are dealing with these distributions of charge, we have Boltzmann statistics, which lead to exponentials. And exponentials will be sort of the basic language for understanding circuits throughout the rest of the class. And it all comes down to the fact that we have the exponentials here in these from this energy band diagram. So this is the source of all the other exponentials we'll see in the rest of the course. Now, yes.
Just quickly, could you maybe explain the Fermi level? Like, why does it move up or down depending on that?
Well, it's really the point at which you have the equilibrium between the concentration of carriers in the conduction band and valence band. So if you just take the difference, this is where everything would be sort of at steady state without having any charge flowing or any energy being dissipated. And yeah, so they are, if you align everything with the conduction band and with the valence band, what moves around is the Fermi level. You can do it the other way around. You can align everything with the Fermi level, which is sort of your zero reference. And if you do that, in fact, that's the next slide. If you put the Fermi levels aligned, which is typically what you would need to do, it's one Fermi level. Then what moves around is the height of the the distance from the Fermi level of the conduction band and the valence band. So in energy band diagram, this would be the proper way of drawing things, to keep the Fermi level always aligned and then put all the other levels relative to the distance. And this is what happens if you put this p-n junction together. So this is going back to this diode. Yes?
Just for the previous slide was exponential from the Boltzmann statistics. Yeah, thank you. For people who do not have physics background, I mean, talking to myself, this is not something that I have seen before. Is it worth to actually spend some time to understand the derivation of these specific things for your course? Or
so it doesn't, it's not like a question of the exam to go into more details than whatever is written here. So just knowing these formulas is enough for the rest of the course. But if you do want to know where they come from, in the first lecture, those extra sets of slides I gave as a reference explain where do these exponentials come from. But from the point of view of understanding the circuits and understanding, how to create a neuron and a synapse and so on, this is already more than enough. It's in fact even too much. So we won't be going any more into details than what is written here at this level.
Sorry, could you repeat what is Ni?
Ni is the intrinsic concentration of majority carriers in a semiconductor. In case of intrinsic, it's equal to square root of n or p. So the product NP is equal to Ni squared. So Ni is the square root of NP.
Okay. And when it's undoped, NP are equal?
Yeah.
Okay. Thank you.
Yes.
Is constant majority carriers the same as mobile carriers?
Yes. Okay. So if we go here, when we put these two things together, and if we just look at it from the energy band diagram, we align the valence and conduction bands. you'll see that there will be basically a difference in concentration of mobile charges. The N-type material has more electrons, and the P-type material has more holes. And if we put them together, this difference of concentration leads to, to the creation of a depletion region, where all of the, because of electrostatic, right? All of the plus charges, all of the mobile plus charges in the P-type material, those are mobile. They can, go away. The fixed plus charges, those are the fixed ones in the N-type material, cannot go away. So you have essentially the fixed plus charges in the N-type material push away the mobile plus charges in the P-type, and vice versa. The fixed negative charges in the P material push away the electrons in the N-type. And because the mobile charges sort of go away because of electrostatic, you create a region that is depleted of mobile charges. Everything is at equilibrium. These pluses and minuses cancel each other out. But because of this sort of difference in concentrations and electrostatics, you have a region where there are no mobile charges. So that's why it's called depletion. It's depleted of mobile charges. And then when you're far away from, as the distance increases, then you go back to sort of the standard steady state case where you have your more electrons on one side and more holes on the other. But at the border, you have a region which is called the depletion region.
Why is depletion regions, let's say, asymmetric?
Because in this case, the N-type, you can see it also from here. It was just a case in which we had more concentration of donors than concentration of acceptors. There was an imbalance in the P and the N, which is actually reflected from the real way semiconductors are done. So it really depends. If you have exactly the same concentration, extra donors and extra acceptors, it would be perfectly symmetrical. But because in practice it's not, we also made the drawing more realistic in that respect. Okay, so because you have this effect of mobile charges going away, that's because of electrostatic. You essentially are equalizing these two forces. You are creating an electric field, which is trying to push things through drift. And then you have a difference of concentrations. You have many electrons here and few here, and you have many holes here and few here. So you have these different concentration, which creates a diffusion current. So everything, of course, in this PN material is static, is at equilibrium. And this can be done only when the diffusion current equalizes out or balances out the drift current. So at equilibrium, you have these two forces that are canceling each other out, and everything then is sort of steady. And just to remind us, because also for me, it's not my sort of field of expertise, device physics. But the formula for the drift equation is shown here. It's basically, it's given by device physics, and it's proportional to the carrier density, the carrier mobility, and to the electric field. So you have drift every time you have an electric field. And the formula for diffusion is given here. It depends on the diffusion constant or the Einstein constant, and then the concentration gradient, the difference in concentrations. Yes?
When you go like forward bias or reverse, which one dominates, the drift or the diffusion?
Well, there you're imposed. So in addition to this sort of built-in electric field that you're creating, if you apply a voltage, like an external voltage, in this case we would be forward biasing it, you're increasing the drift. So you're having current because of drift.
This is reverse.
Yes. So sorry, in the reverse bias, exactly, yes. So if V is here, this is reversed.
So which one is the diffusion or the drift?
In reverse bias current, everything. Well, there is this dark current, which I guess would be still also due to drift. So in reverse bias, let me think. you're basically creating electron hole pairs just because of thermal fluctuations, and then you have some current. It's because there is an imbalance, and I think it's the drift that is higher than the diffusion. But don't count on it. You should ask Toby. Toby's really the expert. Yeah, and so if we want to really balance these two currents out with formulas, these are the ones that are defining, what is the drift current and what is the diffusion current. And yeah, as I was saying, D is the Einstein constant, which is basically KT over Q times the mobility. So KT over Q is the thermal voltage, and mu is the mobility of the carrier. So either the holes or the electrons, they have different mobilities. So we can think of this built-in voltage difference that comes from putting together P and N material as an built-in potential, which essentially is like an energy barrier. So if we put this P-N junction thing back into the MOSFET, you have a P-N junction on the left, a P-N junction on the right, and so you have your intrinsic, P substrate, not intrinsic, but your P substrate here. So this is what the valence bands would look like if you just have everything connected together with zero differential voltage everywhere. So the source, the gate, and the drain are all connected together, and they're all connected to the substrate, to the reference voltage. And so there you see you have basically an energy barrier that is the barrier is between the source and the drain. It's not allowing charge to flow from left to right or from right to left. And in order to have current, you would need to overcome this energy barrier. So you can think of it like that. And this is, again, a drawing or a movie that Toby made to give you the idea of what's happening. It's always, sorry, I wanted to just show this one. This is the case in which everything is zero. I don't know why it's switching. I think it's still the case. Yeah, the first case was this one. Let's see if it switches. Oh no, it's okay. So basically you have a small gate voltage or gate to source voltage difference, and then you have a zero difference in the drain. So the concentration of electrons on the left is equal to the concentration of electrons on the right. And you can have, because of thermal fluctuations, you can have some electrons that jump from left to right, but on average, the number of electrons that go to the left is the same as the number of electrons that go to the right. So on average, you have zero current flow in the channel. So here. Now, if we have a larger VGS, but still with zero differential voltage between the source and the drain, you decrease the barrier. So on average, there will be more electrons flowing across the barrier, but the flow is going to cancel each other out again because there is basically the same concentration left and right. So the net current, if you're just measuring current with an ammeter through this device, you're going to measure zero, even though there will be actually electrons going back and forth from left to right and right to left. Now, what's interesting, yes?
Why does the barrier go down?
That's because the energy level is the opposite of the voltage. So if you have a positive voltage, you decrease the energy.
Is there an equation for this, or like we just know?
No, there's going to be an equation, but it's essentially, it was also, let me see if it was in the equations that we saw before. Yes.
That is just repeat that for NFET.
This is NFETs, yes. So the positive voltage is decreasing the energy barrier. PFETs, you have always to remember it's the other sign. So you should decrease the voltage to decrease the energy barrier. But there will be equations. I will also show you later with the equations that basically describe this. Now, this is the case. This is the interesting case where you have drain to source voltage difference, which is greater than zero. So you're changing the concentration on the source and the drain electrons, and then you can have electrons flow. Now, if the energy barrier is high, this will be a very small number. But if you increase VGS, like it's shown here, and you have a small energy barrier, then you will have lots of electrons that flow and more in one direction than in the other. And again, this relationship between the energy barrier height, which is proportional to the voltage, and the number of electrons flowing is exponential. And again, it's because of Boltzmann statistics and because of diffusion. We're changing the concentration gradients. And from that, from those equations and the carrier concentrations, those exponentials basically give rise to exponential relationship of current, which is basically the flow of electrons. So if electrons flow in one way, the charge is going in the opposite. So current is always flowing in the opposite direction of electrons. Just that's another sort of convention to remember. And this is how essentially how this MOSFET physics works. This was hypothesized in the 30s. It was sort of experimentally verified in 1947, and then it started being used to actually do computation in the 70s. And actually, then in the 70s, the way that, because the devices were big and it was very noisy and things, the way that the technology led to creating digital circuits, basically saying we just use the maximum so that we can have a very large current flowing or no current, essentially no current flowing. And that's how digital technology became predominant. But in the 50s, 60s, 70s, the number of digital circuits and the number of analog circuits were more or less equivalent. Only from the 70s on, the digital way of doing computation became the predominant one, and still today it's a standard way of doing computation. So, however, this idea of having different concentrations of carriers and using diffusion to control or using the energy levels to control the amount of charge flowing from one side to the other is the same that was observed by Hodgkin and Huxley when they were trying to understand how neurons produce action potentials. So when Hodgkin and Huxley, again in the 50s, were measuring from real neurons, they were basically, what they did is they basically put some electrodes inside the cell, and they measured the activity of the cell by basically trying to understand how much is the current flowing from inside to outside. The way they did that is that they have this, what is called a voltage clamp. This is what led to the Nobel Prize. They put these electrodes inside the cell, and then they had, through an external oscilloscope, they had a device that would change the amount of current in order to always keep the difference from inside to outside constant. So clamping the voltage to some constant value by, if the neuron is changing, its properties by changing the amount of current that is necessary to push in or out of the cell. So they were essentially counterbalancing. If in the cells, it's not electrons that flow from inside to outside, but it's ions. And in this case, it's sodium and potassium ions. So they're positive ions. And the flow of sodium and potassium was counterbalanced by this current in a way that it was always sort of making sure that the voltage difference was always constant with this voltage clamp. And by doing this and then letting the neuron do its own dynamics and letting it run, they observed that the current due to sodium was, some inward current, and then the current due to potassium was another inward current. So they actually could measure the sodium and potassium currents by essentially using this electronic circuit with the voltage clamp device. And then they actually measured as a function of the difference between the potential between the inside the cell and the outside of the cell. And this is what they measured. So they applied the potential difference of few millivolts from inside and outside, and they measured how much current would flow, or in that case, the current is proportional to the conductance. So here they're plotting conductance. How much is the conductance change as a function of the delta V? So we have a plot here with V, delta V on the x-axis, and conductance values, semi-log conductance values on the y-axis. Because it's a semi-log plot and we have a line, it's a pure exponential. So also in this case, we have exponentials, and you can imagine the reason that you have flow of sodium from inside to outside is because the concentration is changing. As the concentration is changing, then you have more or less flow of sodium. This is to show you, if you plot you'll see the data, but if you plot the subthreshold flow of current through the transistor channel, not the protate channel, you have much less gain. And in computation and in computing systems, gain is power. You know, the more the gain you have, the more you can be robust to noise. So this is just to make you realize that nature is still much, much, much more efficient than any artificial system we can build, because of this very big difference in gain. So even though we can still replicate the physics through diffusion, and we can get lines with which represent exponentials on a semi-log plot, we are still not able to build devices that are as efficient as cells, as biological cells. And this is with CMOS technology, but there's you know, all the other technologies are also lacking behind. CMOS is actually the best one in terms of the gain that we have. But there is organic electronics, there's DNA computing, there's all sorts of other alternative technologies that are being investigated that do not reach this level of efficiency in terms of computational power. So yeah, so this is basically the analogy between neurons and transistors. They both depend on Boltzmann distributions. It's nice, they both have these exponentials, so we can really replicate the physics of cells by using semiconductors, you know, p-n junctions and MOSFETs. In neurons, the current is due to these ionic conductances that change exponentially. So it's due to the sodium, potassium, and other ions that flow from inside to outside of the cell. In transistors, it's really due to these electrons and holes that are depending exponentially on the barrier height. And the populations of carriers depends exponentially on the barrier height. And here the population of open channels depends exponentially on the delta V, on the difference across the barrier. So this is again to remind you what Hodgkin and Huxley measured.
Oh, sorry, in the slide before, what's E-fold?
E-fold is how many values it changes with the E number. So let me see if I can go back. Oh, it's going forward. Yeah, anyways, it's basically every E in the semi-log plot. So every step in
Oh, okay.
yeah. So yeah, I don't know why it's not answering to my commands. I don't know what's happening. But yeah, so no, it's going forward. Page up is not working. P for previous, nope. Let me see if I can control the slides. Okay, so we were here. As I was saying, this is just to show you again the data that led to the Nobel Prize of Hodgkin and Huxley. It's 1952 measurements. And from these measurements, they derived the equations that then led to their model for how neurons generate action potentials. But the important thing is to remember that it's the same physics. So if we can reproduce essentially these physics with transistor channels compared to ionic proteic channels. The one thing to notice is the difference in mobility. So ions have a much smaller mobility than electrons, you know, factors of thousands. So in addition to having a lower gain, the silicon is much faster. So we can either think of that as a bug or a feature. We could try to exploit it, but that's another big difference. The gain in this curve and the mobility, so the speed of how quickly things flow from across the channel. Yeah, so to summarize, yes.
How did you get from
Oh, it's not shown here, that's why. Yeah, no, here it's not shown. You cannot compare the mobility from this diagram. This is just plotting the currents. So the dynamic part is not shown. Yeah, so this is just to summarize. Whenever you have an NFET, you have all these symbols. The source, the drain is called VG, VS, the gate is called VG, the source is VS, the drain is VP. The substrate is P minus, and if you remember, I told you that it's always connected to the reference voltage, which is usually denoted as ground, and it's usually 0 volts. In order to connect whatever is below the substrate of this wafer of silicon to the voltages that are running on the chip, we can then create, sorry, it's the first time I'm using this thing, I always have trouble. Okay, here. We can then create an ohmic region between the substrate and then some terminal, which we can call bulk, the VB. And then we now have access to the reference voltage. We don't have to sort of go from below the wafer. We have access to the reference voltage as a metal line together with all the other metal lines. And this is, as I said, by default, is connected to ground. And all the reference voltage of N-type transistors is always ground. So it's usually it's always the differential voltage that you're measuring. Vs minus the reference. So Vs minus ground or Vs minus 0. So for simplicity, people just write Vs. Vg minus 0 and Vd minus 0. So in case of NFETs, the reference voltage is 0 and people just never write the differential version. They just write the absolute value, but it's the same, right? In case of PFETs, the reference voltage is VDD. It's the power supply line. So in that case, you do have to write it. It's VDD minus VG, VDD minus VS, and VDD minus VD. So if you're talking about PFETs, you do have to write the full thing if you want to really make equations make sense. The other thing that's denoted here is this double dot dash line. So this is denoting the depletion region. Remember, we have p-n junctions, and when we put together a p material with an n material, there is a depletion region that's there. And you can actually, depending on the difference in concentrations and so on, you can think of it as thicker or thinner. So it's important to remember that there's this depletion region also in NFETs because it's made of p-n junctions. The other variable that is shown here, which is important, is this Phi-s. This is called the surface potential. It's the potential that is just under the channel, the potential at the surface of the silicon, and that's going to become important in the next equations. So yeah, so this is just terminology, and maybe before we go on to the next equations, we can have a short break, and then we can carry on after the break. Maybe a 10-minute break at 3:10. We can start again. So just to remind you about the physics, there's an analogy between the transistor, the source, the drain, and the gate, and just flow of water in buckets. So you can think of the gate as if you're opening the sink and then of a tube, or opening the level of a tube, the barrier of a tube, and then the source and the drain as the two buckets of water. And if they're at the same height, you can open as much as you want and nothing will flow. But as soon as you change the potential difference, so one is higher than the other, you will have water flowing through. So this analogy maybe helps in understanding that you can have current flowing through only if you have a VDS difference, a difference between the drain and the source, and only if the gate is allowing the current to flow, if the barrier is not too high. So you need these conditions. You need to have a positive gate voltage or gate to source voltage, and a difference in drain and source potential. That will allow your electrons or holes in the same to flow from the drain to the source or vice versa. So yeah, that's just to remind. The other thing I wanted to remind everyone is about the lab handouts. In the previous years, we would do it in the lab with equipment, and everyone was expected to write a PDF report to hand in to explain, the measurements. This year, and actually already from last year, we started using Jupyter Notebook. And so it is sufficient if you fill in all the Jupyter Notebook, answer all the questions, put in all the plots in the notebook, and then you export it. If not in PDF, at least in HTML, and then upload it on your Dropbox. So you don't have to write a separate report, but it is individual. We have to evaluate all. So every single one of you has to put your own individual report, even though you use the same plots from the measurements if you work in teams. So make sure that everyone uploads the exported version of the Jupyter Notebook, and maybe for completeness, also the original, the source of the Jupyter Notebook. Then it's everything is there. Okay, so going back to transistors, let's see where we are. So the regimes of operation of the transistors are basically these. Whenever your gate to source voltage is 0 or negative, you're in this cutoff region where the surface is accumulated. You're actually pushing away electrons even more. So in addition to not having them because there is depletion region, you actually have even less. So you're basically really switching off the transistor. Then when you have a very small gate to source voltage, you're in this weak inversion regime or subthreshold regime, where you're allowing current to flow through diffusion if you have this difference in potential. You change the concentration gradient from drain to source and vice versa. And then this is the one that you saw last week, the above threshold, the strong inversion regime, where you have an electric field and you're actually pushing electrons or holes through due to drift. So that's the one that you saw last week. And in this course, we will be studying essentially the circuits that work in subthreshold. This is quite uncommon, and that's why, and it's sort of because of these exponentials similar to what happens in biology. So this is why there's this particular course offered here, and of course it's complementary to all the other ones being offered at ETH for standard electric design or electronics curriculum. So now, in terms of if you measure these currents from a transistor, this is what you would observe. I think I already showed this plot before, but essentially when you have small gate to source voltages, this is when we are in this weak inversion or subthreshold regime, and this is when you have exponentials. And in a semi-log plot, that means you have a line. So this is actually data from an old chip that we actually measured, and we applied a relatively big VDS, so we had a difference in potential, and then we changed the gate voltage. And by changing the gate to source voltage, you see how you have this pure exponential relationship between the output current, the current flowing from the drain to the source, IDS, and the gate to source voltage, VGS. And you see it's a relatively small range. It's between 0 and 0.8, 0.7 volts. So it's like a 700 millivolt range of operation of input, but you have a huge range in output. You go from, femtoamps, 10 to the minus 15, to microamps, and maybe even, fractions of milliamps. So you span several orders of magnitude in output with very small changes in input. And we have millivolts on the x-axis and maybe nanoamps, if we just stay here in the middle, nanoamps on the y-axis. Yes?
This is a diffusion current.
This is diffusion current, yes, yes. The mechanism of carrier transport in subthreshold is diffusion, and that's why we have these exponentials. And because of these millivolts and nanoamps, you can imagine the power consumption of this device is extremely small. We have, fractions of nanowatts. So a single transistor can be very, very efficient in terms of power consumption. Now, what is the catch? What is the price to pay? The catch is, as I told you, it's quite uncommon. It's unusual. If you go to standard electronic courses in the various ETH or around the world, most courses are teaching how to design circuits in above threshold, in strong inversion, which is this region here, where you have this quadratic term. So it's a quadratic relationship between the gate to source voltage and the current, but on a semi-log plot, you get this sort of saturating effect here. But in a linear plot, you would see a parabola. And as I said, most courses teach how to do, and historically, from the 80s on, the analog design courses are teaching how to use transistors in this region here, where you have relatively large voltages and relatively large currents, milliamps, 10 to the minus 3. And the reason is that if you have some signals that are noisy, if you're doing analog, you want to do your hi-fi equipment, and if you have some noise, which is making your input oscillate, say between 3.5 and 4 volts, you have some huge noise here. The effect on the output is relatively small. You're compressing the noise. Sorry. Oh, this is not working. So that's why for analog design, you you can have precise computation at the cost of power. On the other hand, if you have the same fluctuations here on the x-axis between, I don't know, 0.5 and 1, you have some noise here, your output current will change by, like 3-4 orders of magnitude. The effect is going to be huge. So you're going to be very, very strongly affected by noise in subthreshold, and less affected by noise in above threshold. That's why standard textbooks, we're saying we care about precision. We're going to do our circuits in this region of operation. And until today, it was not a big problem if you're burning up some power. You just plug your hi-fi to the socket of the wall. But now power consumption is becoming a very important issue in sort of all of electronics, even our cell phones. Our batteries are burning out much more quickly. And even the analog circuits are now being designed in a way to reduce power consumption. So it became quite popular to study how to do computation using circuits in subthreshold. So more and more universities and courses are also moving on to subthreshold. The other reason is that if you realized, the power supply rails have been decreasing with the technology, with Moore's law. So this is a very old chip in which the power supply was 5 volts. But then the more, like 5-10 years ago, the power supplies went to 3.3 volts, then to 1.8 volts. This device probably is working at 0.7 volts of power supply. So then just by trying to reduce power everywhere, everything now is getting much, much closer to subthreshold. The region in which you can use your standard electronics is getting smaller and smaller. And so people are also moving into subthreshold for that reason, that the dynamic range in the input is much smaller. Carver-Mead was the first to say, but this is actually, transistors are not switched off. If I have something that is nanoamps, it's not 0, and I can still use this range in output if I do something, fancy that is somehow robust to noise. And this was in the 90s. That's what Carver-Mead was saying. Let's just try to use this. And because it's close to what real neurons do, let's try to use the same tricks that biology uses to overcome the noise. And so this neuromorphic field comes out of that. But anyways, going back to MOSFETs, we're going to be doing circuits next week, actually, that use this relationship. And we're going to mainly see how to do circuits that exploit this relationship. And again, this is going back to reminding you what you just asked, that the current is because of diffusion, and there is the basic relationship is this Einstein constant with the difference of concentrations. The depletion region here is something we have just by construction. It's not like we can control it. It's there because we're putting together P and N material. The dashed line, or the region between the active area and the dashed line, is only showing the depletion part of the P material. That's the region where you have no electrons. Of course, there's going to be a depletion region in here and in here, but we don't care about that. So this depletion region here is basically saying we don't have electrons. And the only reason we have current is because electrons are shooting across from the source to the drain because of the difference in concentration. So it's this diffusion that's just pushing electrons from the source to the drain, even though there are no electrons, under the channel because of this depletion region in weak inversion. Okay, so this is what you saw for last week when you have. Oh no, sorry. This is going more into the details of diffusion current. So what really counts is for understanding how to really calculate how much current you have is this surface potential. This is basically it's telling you, what is the height of the barrier by looking at the voltage on the source, the voltage or the potential on the source, the potential on the drain, and the surface potential. That's really the place where you have to compare to be able to see what is the barrier. And so these are the sort of the formulas that are telling you what is the potential on the source, the potential on the drain. It's really, definitions that are depending on the charge, the surface potential, and the source voltage, and the drain voltage, and the surface potential. So this is just basic definitions. And then if you write down the diffusion gradient just by taking the difference between the source and the drain and the length of the transistor, which is this L. We just make a very crude approximation of a derivative. Then you can start writing the equations. Yeah, with the concentrations, if you remember from those equations, it's this exponential, with the surface potential, and then we finally get to this equation here. Now, this is the precursor to the equation you have to remember. So again, it's using some device physics terminology, but it's not yet the final equation that you need to remember. But it's important to notice that the current through the channel here depends on the surface potential, which is like, opening or closing the sink, and then the difference between the voltage on the source and the drain. So these two are, again, these exponentials basically tell you what is the difference on the two sides. And the surface potential is telling you how high is the barrier. So how much I'm opening or closing the flow of carriers. So also you can multiply everything together. So you would get two terms. You would get I0 e to the phi s over ut times the first part. That denotes current going forward. And then minus I0 e to the phi s ut times the second part, which denotes the current going in the reverse direction. So you all remember, you always have electrons going one way and the other way, except that when you have enough drain to source voltage difference, you have the forward component dominates over the reverse component. So the net flow is greater than zero. As I said, this is the precursor to the equation you have to remember, but it's an important one. So the only thing now that is missing is how is the surface potential related to the gate voltage? Because whenever we, try to understand circuits, we have access to the gate voltage, not to the surface potential. So if we can just put the gate voltage in addition to the drain and the source voltage in the equation and get rid of this unknown, then that would allow us really to study circuits. And so in order to understand that, we're going to take a cross section here and see what happens when we change the gate voltage, what happens to the surface potential in this piece of material where we take the cross section. And so here, this is the zoom of that cross section. We have our polysilicon, our gate oxide, our gate voltage. The surface potential is just below the gate oxide. And then we have the P substrate. And this is, remember, if VG is in between 0 and 0.8 volts, we have this depletion region where we only have fixed plus charges and all of the mobile holes have been pushed away. Okay, so when we have VG less than 0, we have mobile electrons there, nothing is happening. This is sort of not very interesting. It's in accumulation. There is no flow of electrons. So that's just called accumulation. It's accumulated with majority carriers. Then when VG is equal to 0, we're in this flat band mode. Again, majority carrier is constant. There's nothing interesting happening. And now when we have VG is in the weak inversion regime, between 0 and 0.7, we have small number of positive charges on the gate, which is pushing electrons away. We have our depletion region. And we only are left with the fixed ions there, which is pushing the mobile charges away from the depletion region. So now we can start to see what happens to the surface potential in this condition here. And this is called the MOS capacitor structure. So this is also, as I said, it's an important concept to remember. And let's see, when VG is greater than VT, then we are in inversion. We actually have a lot of charges. We attract electrons. And so we basically have, increasing the conductance of this structure. So in inversion, mobile electrons are reduced at the surface, and the surface is inverted because it should be P minus, but actually now it has more electrons, so it's equivalent to a N minus. So it's inverted in that sense. Yes.
And do the mobile electrons only come from the substrate, or do they also come from the source and drain?
That's a very good question, because they do, in this case, there are no source and drains. This is just a pure structure. But in order to get mobile electrons easily, it would be convenient to have the source and the drain, which are the sources of electrons. That's where they get them from. So if you have to do a MOSCAP in practice, even though you never use the drain and the source, you need to put those active areas, because it's just a place where to get electrons from. Otherwise, it would be difficult to get them from the substrate. Yeah, so basically this is summarizing the sort of the explanation that if we have a depletion capacitor, you can create it by putting together the polysilicon, the insulator, and then the semiconductor. And then if you have weak inversion voltages here, you have this depletion region. And now essentially you have the structure of a capacitor, because you have a conductor, an insulator, and a semiconductor, so another conductor. And now if you notice, you actually have two insulating regions. You have the silicon dioxide, which is a perfect insulator. That's denoted by COX. It just, yes.
And the last slide, is that strong inversion?
No, it was all still in, yes, sorry, that was the strong inversion. With VG greater than VP, that's strong inversion. And here, when we have the weak inversion, again, you have basically these two insulating regions between the two conducting materials. You have the insulator, which is a perfect insulator, and that gives rise to a capacitance which is denoted by COX. And then you have this other region which is depleted, so it's also insulator in that sense because it has no mobile charge. So the depletion region also has an equivalent capacitance, which is called C depth. And if you plot the capacitance as a function of the gate voltage, you see that when it's in accumulation mode, it's constant. There is no charge that can flow. In the depletion, in the weak inversion mode, it actually changes. And the reason it changes is that the thickness of this region here changes with the gate voltage. The more positive charge you have, the more electrons you push away, the thicker or thinner the depletion region is. And if you put two capacitances in series, the equivalence capacitance is smaller. So you get this bump in the capacitance as a function of the gate voltage. And then when you're back in strong inversion, you attract mobile charges there. So your semiconductor is conducting all the way through. Yes?
But as you push away electrons, the more...
Sorry, you're pushing away, I made a mistake, holes.
As you're pushing away holes,
yes,
you're getting more negative fixed ions. So the charge increases also. Because you say that the D, basically D, the distance is increasing, but the charge too. So it should be.
The charge, well, these are always there. They're there even with or without their mobile holes around them, right?
But you say that you push away, so this goes.
This region gets thicker. This insulating region gets thicker.
But you see that three new ions are there.
But they're fixed. They cannot move, so you cannot have current. It's not mobile charge. It's not. It doesn't allow the capacitor to charge or discharge because they're always there. They cannot move. So there is no dq. There is q, but dq is 0.
But sorry.
There's still charges accumulating in the gate, right?
Yes, those are fixed with the VG. So if we just fix VG here, we have some. It's at equilibrium, right? The charges that at the gate create the thickness of the depletion region. But also those are, I mean, if we just have a fixed VG, also those are fixed. Was there another question?
Why the capacitance grow instantly when the channel forms?
That's due to this exponential, I think. Actually, I don't know the details myself. I don't know if this is a faithful drawing that Toby made, or it probably is. So there is this asymmetry, and it might be related to this exponential, that the positive exponent is larger than the negative. I actually don't know the details myself. Yes.
Sorry, can I just show you like on the screen?
Sure.
Okay. Sorry, but like we agree. So yes, at the beginning there, you have only these charges, and then it gets wide. So you have 1, 2, 3 new charges. So you have a DQ.
Oh, no, well, but you have to, let's say I fix VG to 0, and I have some depletion region.
Yeah.
Then I fix VG to 0.5.
So that gets wider.
Yeah, but it's,
Okay. So you have 3 new fixed sides.
yes, but I fix, so it's like taking snapshots at steady state. I'm not moving VG back and forth. I fix
Okay.
it. And then I have a snapshot with another VG, and then a fixed VG, another fixed VG. Yeah, of course, if I move VG back and forth, I have flow of charges. So
Okay, so I don't understand.
so it's really putting a constant gate voltage and seeing what happens for different values of the constant gate voltage, but it's like taking snapshots.
Okay, but at every snapshot, there is a different amount of charges on the two
On the
gates.
gates, yeah, and a different thickness of the depletion region. Yes.
So when DG increases, the depletion region becomes bigger.
To some at some point, and then it's so as soon as it starts attracting electrons, it gets smaller and smaller and smaller again. And in fact, as soon as there is some electrons in the just underneath the surface, those are mobile charges, and they can move left and right. Yeah. So as soon as you have these electrons here, then the thickness of the depletion region is 0.
And that's going the curve first.
Yeah, it's good. It's good that we have these questions. Yes.
So practically speaking, how come the curve of current doesn't go down? Basically, when you pass the threshold, why does it still increase the intensity as a factor of gate voltage if you have electrons which are being attracted into the depletion region?
Are you talking about this current?
Yes.
Why does the current not go down when you when you go in strong inversion?
Huh?
When can you repeat your question?
You just said that when you go beyond the threshold voltage,
Yeah.
right, at the gate, you have the depletion region which starts to shrink,
Yes.
right? Because it attracts electrons. Okay, maybe another.
Yeah. So this is the current from the source to the drain on the surface, independent of the thickness of the depletion region. This is really how much current flows because of the diffusion and of drift. So on the surface. And what I'm plotting there is the capacitance, which is not current, it's just the capacitance as a function of the gate voltage. So the x-axis is the same, but the y-axis is different. Yeah, and in this case, it's really measuring current from the source to the drain. In the other case, it's just looking at what happens at the value of the capacitor.
Okay.
With no current flowing from source to drain. Yeah.
Why is it VGS and not only dependent on the gate voltage?
Oh, that goes back to these movies that Toby was making. You really need to do it relative to the source and the drain and the gate. The barrier has to be small. So it's either the barrier between the source and the gate or the barrier between the drain and the gate.
Oh.
But the barrier between one of the two terminals has to be smaller. So that's why it's VGS. It's always a difference. Okay, so we go back here. So now we can, if we agree that there is basically these two capacitors, the one is the fixed capacitance, is the insulator capacitor, which is Cox, and the other is the depletion capacitor, which is CDEP. Then we can see what is the relationship between the surface potential and the gate voltage. And essentially the surface potential is the node in between these two capacitors. And if you write it, it's called the circuit is called a capacitive divider. So the surface potential is in between, and then we can actually, we want to know what happens, how much does the surface potential change when I change VG. I have control over VG, and I want to know if I double this, what is the effect on the surface potential? So you know, if I change VG, how much does PS change? And that's done here. It's basically it's this equation, and because of this capacitive divider, essentially you can write it as this term here: Cox divided by Cox plus CDEP. And this is if we have a constant depletion region, this is a constant value, and we can call it kappa.
So what is the top plate of the depletion capacitor?
The top plate of the depletion capacitor is the surface, is the interface between the silicon and the so Si and SiO2 and the insulator.
So it's also the bottom plate of the oxide capacitor, right?
Yes. So this is the same. So the charge here is the same. The bottom of the oxide capacitor is the same of the top of the depletion capacitor.
So if I apply a positive voltage on the gate terminal, there should be a negative charge on the bottom plate of Cox, right?
If I no, you're pushing the electrons away. You're pushing.
So you should have negative charge on the bottom plate of Cox, but at the same time you will have positive charge on the top plate of C depletion, right?
Yes, you have positive here and negative here. Yes.
But you told that it is actually the same surface, right? So how you can keep negative and positive charge at the same time?
Well, it's the bottom. It's the one here on the, so VG is the top. That's the semiconductor, and then Phi S is at it's below the Cox. So it's the, sorry, VG is the polysilicon, it's the conductor, and Phi S is the semiconductor. So there are two different materials, and you can have positive charge on one and negative charge on the other.
Okay.
Yeah, because there is this insulator in between. And so this equation that tells us how much the surface potential changes with the gate voltage is essentially a constant, which is kappa. And if you think of it, it's always something which is less than one, because, you know, independent of what Cox is, it's some number divided by the same number plus some extra number. So in practice, this kappa, if you measure it, it's something between 0.6 and 0.8. It depends on the thickness of Cox and the thickness of CDEP. Yes.
So if we control the size of the depletion region capacitor with VG, how can kappa be constant?
Yeah, it's an approximation. So for a constant VG, it's a constant kappa.
Oh, okay.
If you modulate VG, the depletion region will be modulated. So kappa will actually change with VG, but it changes by a little bit. So it's, you know, 0.6 and 0.62 or 0.58. So to first approximation, we can consider it constant independent of VG, even though you're right, it is being modulated by the amplitude of VG. Yeah, it's a very good point. So yeah, so here we go with the charge. Exactly, the charge, the question that was asked through Zoom, the charge is the same at the bottom of Cox and the top of CDEP is the same charge Q, and we can apply just the, you know, the charge constancy equations and derive those equations that I wrote before. So this is how we get this kappa. The charge is the same, so then we get this kappa. And in practice, this kappa has the effect of changing the slope of that curve that we plotted where we, sorry, this is again, it's just graphically explaining, the slope kappa is the relationship between the gate source and the surface potential, the gate voltage and the surface potential. And in practice, let me go straight to the plot. In practice, it determines the slope of this curve. So the slope of this curve is kappa over UT. UT is the thermal voltage, again, to first order approximation at constant room temperature is 25 millivolts. Kappa is about 0.6, 0.7, and that's how you get your thing. So now the important equation to remember is this one. So if we replace that relationship of surface potential and gate voltage with the kappa, we can actually put it in the equation here. And this is the important equation to remember. So this is sort of probably the most important slide in the whole lecture, that the current flowing through the transistor channel in subthreshold is exponentially proportional to the gate voltage times kappa, and to the difference between the source and the drain voltage. And these two contributions of the current you can write as forward and reverse currents. So the forward current is the one going from the drain to the source, and the reverse current is going from the source to the drain.
Sorry, I think like the first time this equation was shown before in the slide previously, it was wrong. It was the opposite way. I just wanted to point it out because it didn't make sense to me.
Was it this one here?
Yeah.
E minus, because of the minus, or?
It was in the previous slide of this, it was forward where it was VD.
Let me see, is it this one, this previous slide?
Oh, no, yeah, in the end.
I actually didn't check, but it seems the same.
It was minus VD UT. Is that forward?
Oh, sorry, in terms of forward and reverse current.
Yeah.
I see. Oh, it could be that we made a mistake here. Yeah, you're right. I think the forward is the minus VS. VGS.
Yeah, because from VD to VS is electron moving, so it's the opposite way.
Yeah, but there is the minus. So the forward current is the one going from the drain to the source, and the reverse current is the one going from the source to the drain. So e to the minus VD is the forward current. It's correct. And so maybe the other one is wrong. Yeah, so here it's putting forward and reverse, but it's e to the minus. Yeah, you're right. There is some mistake somewhere. But the drawing is correct. The forward current is the one going from the drain to the source, and the reverse current is the one going from the source to the drain.
Yeah, the writing is right. Like in the previous one, the other one, it's the potential of the surface. So if you multiply its potential of the surface minus potential of the source, and like I think the minus is correct. It's still referring to the source.
Yeah. So VGS is the forward current, and VGD is the reverse current.
So the other one was wrong.
Okay, so the other one was wrong then. Yeah. So VGS is the forward current. So this is correct. VGS, if we put IF to the first term here, it's the forward current, and VGD is the reverse current. So this is written down here. So this is correct. I0 is the current that you would have if you had a 0 VG. So it's typically, depending on the process, but with this old chip, it was 10 to the minus 15, 10 to the minus 14 amps. So 10 femtoamps. VD. In this case, we are assuming probably when we took this data, it was anything above 100 millivolts, VDS. I don't know what Toby wanted. Okay, yeah. Now Toby is saying, how do we actually measure the threshold voltage that determines the region between subthreshold and above threshold? And this is the way to do it. You basically can just fit a line with the line of the exponential that you have, and then have when the current differs by 0.5 of the extrapolated value from the actual measured value, that is defined as the threshold. And then you go back to the gate to source voltage. That is the threshold voltage. And as I told you, depending on the process, that also depends. You can see it depends on the slope and it depends on I0. So it depends on the process parameters. It's something typically between 0.7 and 0.9 volts. It's another thing that you can consider as constant. So if you have inputs to your transistor that are below 0.8 volts, you're pretty sure you're in the weak inversion regime. You're in subthreshold. If you have inputs that are above 1 volt, you're definitely in strong inversion. So now we can actually simplify the equation. We can multiply e to the minus Vs and take it outside of the equation, so that we have e to the kappa Vg minus Vs outside. We have a 1, and e to the minus Vd minus Vs here. So we just did some algebra. We just collected the e to the minus Vs and put it outside. And then you get a 1 here, and then you have e to the minus Vds here. So if you have Vd minus Vs, for simplicity, you can write it Vds for in short notation. And this one, you have to have kappa Vg minus Vs, because there is a kappa that's only multiplying the Vg and not Vs. So now you see that this is sort of the full equation that we derived from all of the previous slides. And now you see what happens if you have enough differential voltage difference. If your e to the minus Vds is large enough, you can actually, there's a minus here, right? So if Vds is great, you have e to a minus large number, and that becomes a very small number compared to 1, and you can neglect it. So then you get a simpler equation, which is basically saying the current through the transistor is only the forward current, which is the e to the kappa Vg minus Vs. Now, how big is big enough? How can we make sure that this is negligible compared to 1? For example, if we have 4 ut, we get e to the minus 4. E to the minus 4 is 0.000 something, I don't remember. And then this 4 ut is a ballpark number that we say is large enough to assume that this is negligible compared to 1. So essentially, we say the transistor is in saturation if the drain to source voltage difference is greater than 4 ut, which is it's about 100 millivolts at room temperature. So if your VDS is greater than 0.1 volts, you can use the simple equation here, and you can say the transistor is in saturation. There's only current flowing one way from the drain to the source. It's only the forward current, and it's really a simple equation. And then you can imagine if you have 2, 3, 4 transistors, you can really start putting together simple equations like this, and then reason your way through the circuit. So now you have to, yes?
Could you repeat which value it is in saturation?
When VDS is greater than 4 ut. If VDS is greater than 4 ut, you have e to the minus 4, and 1 minus e to the minus 4 is essentially 1. It's approximately equal to 1. And 4 ut is a nice number because it's 0.1. At room temperature, it's 0.1 volts. It's 100 millivolts. That's why we use, I mean, the community uses this, this convention. Yeah, so when we cannot say anything about VDS, we have to be careful. We don't know if VDS is greater or smaller than 4 ut. Then we have to use the full equation, which now in sort of simplified terms is this one. And then if VDS is greater than a few ut, like 4, then we can use this one. Now, these are the ones to remember. It's really easy to remember them. You should notice that to simplify our life and to make the notation shorter, we got rid of the ut. We actually are assuming that we are always dividing by ut. So you just have to remember that when you see these, this is actually, the exponent should be dimensionless. So it's a voltage divided by UT. But just for simplicity, we are assuming that V is in UT. Whenever you see these equations, it's because it's not that we made a mistake. It's just that we're lazy and we're assuming that we are dividing by UT. Now, what happens when you change the VDS? So you can change VGS or you can change VDS in these equations. Well, in the equations in the previous slide, if I could only go back. And this is showing you how the current changes as a function of the drain to source voltage difference. And you see that as long as you're above your 100 millivolts, it does not change. That's the assumption we're making. The current only depends on the VGS. There's only forward current, and there is nothing, it's so small that you don't see the effect of the VDS if it's greater than 4 UT. So the current only depends on the gate to source voltage, which is giving you that exponential plot that we had in the previous ones. But when you are in the so-called triode region or ohmic region, then the current does depend on the VDS, and it's more or less, you can approximate it to a line. So it depends linearly to the VDS. So there are basically these two independent regions of operation of a MOSFET. Subthreshold, above threshold, which depend on how big your VGS is, and ohmic region or triode region and saturation region, which depend on the VDS, and they're independent. You could have subthreshold in triode, subthreshold in saturation, above threshold in triode, above threshold in saturation. So you just have to remember these different regimes. So if your VGS is below the threshold, you're in subthreshold, and if your VDS is above 4 UT, you're in saturation. And you can use the very simple equation that the output current I is equal E to the kappa VGS. Oh, I0, yeah, someone was asking about I0. Here's the full thing about I0, where it comes from. So it really depends on all these parameters that are depending on the process, the carrier concentration, the thermal voltage, the diffusivity, and this E to the minus kappa VT over UT. But again, this is also way too much detail. You just need to remember it's the off current, it's a very small current that always flows. Even if you put a 0 gate voltage, you always have this current. It's called also the leakage current because it leaks through the transistor. And I think that was the last slide. So we're just in time. So we're just from the point of view of what this transistor do as a functional behavior. The VG is allowing you to change the transconductance of the transistor. So if you see how much does the current change as a function of the gate voltage, DI over DVG, that basically tells you what is the transconductance of the transistor. And you can do the same, you can use that very simple equation and then calculate what is DI over DVD. How much does the current change versus the drain voltage? And how much does the current change versus the source voltage? So that maybe I could leave as an exercise. It's really simple. It's very simple equation and it's an exponential, so you can calculate the derivative really easily. But that's basically telling you in terms of how much does the current change as a function of the voltage, that's giving you a conductance. It's equivalent, it's a equivalent conductance. And the one calculated for VG is called transconductance, and then the other one is called drain conductance and source conductance for obvious reasons. And that's going to be useful, handy to know when we try to analyze circuits. And so we will start looking, this is the same for the PFET, and then we will start looking at circuits next week and trying to use these equations to understand, what do the circuits do? Once we put these things together, how do they work? So we'll go really into all of the details of a source follower and many other circuits next week.